Now we'd like to look at a few more Laplace transform properties, and in particular, one of the most important properties of the Laplace transform that is kind of one of the main reasons we study Laplace transforms when we're looking at LTI systems, or why Laplace transforms are kind of the right tool to look at LTI systems. So we'd like to be able to understand properties of the Laplace transform and then, of course, use those properties. So the most important property or fact about the Laplace transform is the following sentence. Convolution in the time domain is multiplication in the Laplace domain. This is like, huge fact. Kind of like the output of an LTI system is the convolution of the input with the impulse response. Also a big fact, or complex exponentials are eigenfunctions of LTI systems. These are kind of these big facts, big takeaways from this class. So we can sort of formalize this in a theorem. If x of t and h of t are two continuous time signals with the Laplace transforms h and x with ROCs RH and Rx, then the following Laplace transform pair holds: h convolved with x is h of s times x of s. So the time domain, here we have the time domain, and here we have what's called the Laplace domain, right? And we're going to see various results like this in terms of, we're going to have the same thing for when you see Fourier transforms, and same thing when you have Z transforms, that convolution in time is going to be equal to multiplication in frequency or in Z or in Laplace. And this is very important because essentially it allows us to look at chains of LTI systems as just kind of multiplying Laplace transforms together. And this is kind of a connection between thinking about systems operating like matrices and this sort of that we talked about a little bit earlier. So it's like acting like a kind of matrix multiplication of some kind. So the ROC of h of x of s, that is the output of this system, is going to contain Rx intersect RH. And remember, the only way it's going to not actually be equal to Rx intersect RH is if we have this pole zero cancellation. So most of the time we're not going to have that. It's going to be equal to Rx intersect RH. So how do you prove this most important property? Well, you just throw in the definition. So here we have the definition of convolution. Right, so we throw in the definition of convolution, and then here we have the Laplace transform. Right, so now we just squish all the integrals together. We have this double integral over d tau and t. We have the tau integral for the convolution, and we have the t integral for the Laplace transform. And now we're going to do a little sneaky thing. We're going to factor out e to the minus s tau from here, and this is going to leak this as e to the minus st minus tau. So this t minus tau is going to match this t minus tau. And then we do something which you have to justify mathematically, but we're not going to get into that right here, which is to swap the order of integration. So instead of d tau dt, we have dt d tau. And now what you can do is this thing in blue, you can recognize this is just the Laplace transform of x, and so we get x of s here, and then this x of s doesn't depend on tau anymore, and so we can pull it out, and so we just get the Laplace transform. So we get here the Laplace transform of h, and then we get h of s times x of s. So it really holds by basically plugging in the definition, swapping the order of integration, and then simplifying. So what does this property mean? It means that we can find the output of LTI systems by just multiplying the corresponding Laplace transforms and then inverting the Laplace transform to get back to the time domain. All right, so how does that work? So suppose we have these two decaying exponentials, x of e to the minus 3t u of t and e to the minus t u of t. Now if we wanted to convolve these two, that is, we want to compute h star x or x star h, we could go back to our template that we talked about when we talked about continuous convolution, and we can say, we can plug it into that formula and get out the answer. And so that's one way to do it, and here's a different way to do it, which is using Laplace transforms. So if I multiply the two Laplace transforms of this, so this corresponds to this Laplace transform, and h corresponds to this Laplace transform. So x is 1 over s plus 3, and h is 1 over s plus 1. And so now we have to expand y out. We have to split apart these two terms. And the way we can do that is what's called partial fraction expansion, which I hope you've seen before, but we'll do a little example here. Hopefully it jogs your memory. So we have 1 over s plus 3 times s plus 1, right? 1 over s plus 3 times s plus 1. And we want to write it as a linear combination of an s plus 3 term and an s plus 1 over s plus 1 term. So how do we do that? Well, to find the coefficient corresponding to the to this s plus 1 term, we multiply by s plus 1, so that as we kind of cancel these two out, and we plug in s equals minus 1, and we get a half. Similarly, if I want to find s equals 3, this term, I multiply by this s plus 3, I multiply by s plus 3, and so those two cancel, and I plug in s equals minus 3, the location of this pole, and I get minus a half. And then my partial fraction expansion is minus a half times s1 over s plus 3 plus 1 half 1 over s plus 1. And then we look at this and say, what does this look like in the time domain? Notice that these two signals here are both right-sided, so we're going to have the answer is also going to have to be right-sided. So we choose minus a half e to the minus 3t u of t plus a half e to the minus t u of t. Right, so if we applied our formula, we could have also done that as well. So another property, we're going to come back, of course, to this convolution property again and again, but now moving on to a couple other properties, we have, just to kind of clean up the end of the Laplace transform properties, we have differentiation in time, or differentiation in frequency. And so if we take the derivative of the signal in time, so you have a differentiator circuit, for example, then this corresponds to multiplying by s in the Laplace domain. So differentiation is multiplication by s. And this is going to be very important when we see the connection between linear constant coefficient differential equations and Laplace transforms. This is where we can just sort of convert all the derivatives to multiplications by s. If I differentiate in the time domain, then, or sorry, in the Laplace domain, then I get minus t x of t. So there's a kind of, there's a sign difference between these two, so they're not perfectly symmetric, but you get this minus t x of t, and it's for a similar reason. And that's because when we do the Laplace transform, we have to we have this minus st in the numerator, in the integral for the Laplace transform. So let's use a little bit of an example. Let's find a Laplace transform of t times e to the minus at u of t. So here. So what you could do is you could say, okay, let me do this from the definition. We have this u of t, and so this integral goes from 0 to infinity, and we plug in, and then we say, oh, okay, look at this integral. We're going to have to do integration by parts, and then you either say, you kind of roll up your sleeves and do the integration by parts, right? Or maybe you make a connection to something you've seen in probability, like the expectation of an exponential random variable. I'd argue that this is kind of the bad way of doing this this Laplace transform, and instead you can just recognize that t e to the minus at u of t is going to come from this second property here, and we're going to just say, oh, well, this is just negative the derivative with respect to s of the Laplace transform of e to the minus at u of t, and so we get 1 over derivative of 1 over s plus a, and this is just going to give us minus the derivative of this, and we're going to get 1 over s plus a squared. So that's actually much simpler to think about. So often where you first encounter Laplace transforms is when you're studying linear constant coefficient differential equations. And so, for example, you have something that looks like 2x of t is d squared dt squared x of t plus 2 ddt x of t. And then to do the Laplace transforms, you just take the Laplace transforms on both sides. So if these two things are equal to each other, the Laplace transforms are equal to each other as well. We get x of s over here. We get s squared x of s because we're taking two derivatives, and we get 2x of s because we're taking one derivative over here. And there's a coefficient of 2. And then you can, gather like terms and rewrite x of s is equal to 1 over s squared plus 2s plus 2 minus 2, which is 1 over s plus 2 times s minus 1. And then you could use partial fraction expansion to go then and find x of t. So I welcome you to try that. And so this is you usually see Laplace transforms, and so we're building kind of on that basis to sort of understand what happens when we have systems. So this is just understanding a single system X, but we're going to want to understand systems. Okay, so that was derivatives, and derivatives correspond to differential equations, but we can also talk about integration. So if I integrate a signal from, so this is the integrator. We already saw before that the integrator system h of t equals u of t. This thing corresponded to 1 over s, and again, indeed, so if I integrate a particular x of t here, I'm going to get 1 over s times x of s. And the ROC is going to contain the original ROC of x plus the imaginary axis. There's a pole, of course, at s equals 0 because there's this 1 over s term, so this ROC cannot contain the imaginary axis itself. And this is going to be important because we're going to see that containing the imaginary axis corresponds to stability for a system, and we know that the integrator system is unstable. So, like, if you take h of t is equal to u of t, then we can see that this integral from this integrator system, this thing here is just the convolution with the unit step function, right? And so we get, as before, the unit step function has Laplace transform 1 over s. And the last little bit of Laplace transform properties, which are kind of useful when we think about rational transforms and limiting values and initial conditions and stuff like that, is if x of t is equal to 0 for t less than 0, and it doesn't have any delta functions or singularities at t equals 0, then if I take the limit as t goes to 0 of x of t going from above, then that's just the limit of s times x of s as s goes to infinity. And if I want to look at what happens when x of t happens to x of t as t goes to infinity, then we can look at the value of s times x of s as s goes to 0. And so these are mostly useful in some problems when you have rational Laplace transforms. That's where we're going to see them in the context of this class. That's where these properties would get used. So, as always, try to do a couple of examples yourself. So find the Laplace transforms and ROCs and draw the pole zero diagrams for a bunch of different signals, and then try to find time domain signals corresponding to the Laplace transforms given here. And I think in doing so, again, you build some more intuition about how operations on a signal, that is, manipulations of a signal, lead to manipulations in the Laplace domain. And again, we'll help build that intuition that we're going to build on to understand sort of what's happening to system properties in terms of what's happening to the Laplace transform.